Hello everyone, I'm Feihu Yan from Beihang University. Today, I will introduce our work, Molecular Depth Slam with Consistent Deep Depth Prediction. I will introduce this work from the three parts. First, I will give a brief introduction. Then, I will give details of our method. And finally, I will show some results. Now, let's start. SLAM is the abbreviation of Simultaneous Localization and Mapping, which contains two main tasks: localization and mapping. SLAM is a technique for estimating sensor motion and building structure in an unknown environment. It has been used in many applications, such as online 3D modeling, AR, and self-driving car. In recent years, SLAM using cameras only has been actively discussed because the sensor configuration is simple, but the technical difficulties are higher than other sensors. Molecular SLAM systems can be divided into feature-based method and direct method. Feature-based SLAM systems, represented by OBSLAM, normally employ handcrafted feature detectors and descriptors, and can provide stable estimation in rich texture environments, while direct method directly using the input image without any abstraction. The feature-based method can only recover sparse point clouds, while the direct method can get same dense maps. However, it's difficult for both methods to generate dense maps. The goal of our work is to propose a dense mapping method for molecular SLAM. The basic idea is to combine the molecular depth prediction network with the SLAM framework. Considering robustness, we chose the widely used OBSLAM tool as the basic SLAM framework to track poses of the moving camera, and we chose modern depth as the depth prediction network. Here we show the overview of our work in this figure. We first use OBSLAM tool to estimate the camera poses and detect keyframe. Then the deep depth estimation network is introduced to predict a dense depth for each keyframe, which is refined to generate the local depth submap. Finally, submaps are fused to obtain a global consistent depth map. To refine the depth prediction, we mainly consider three types of regions that are likely to cause uncertainty for depth estimation. The first type is the area near the image boundary, because the depth estimation network is trained by the laws that enforces left-right depth consistency. The image area close to the boundary will have great uncertainty, and we will directly discuss this part. The second type is the area close to the contour of objects. We can observe that the depths of these areas are over-smoothed. So we use a filtering method to refine the depth. Using this filter, areas with sharp color or depth changes will be enhanced, while the other areas with little change the information will be smoothed. The third type is the area far from the camera. Following outline 2, we consider points with depth greater than 14 times the baseline at 5 points, and discard this point. Due to the occlusion and other situations, it is difficult to avoid outliers in the predicted depths. Here we compute the local outlier factor for each point, and points with score greater than 1 are treated as outliers. We use the SAP method to align submaps and generate the global depth map. It is worth noting that the SLAM system is constantly optimizing the map, but the depth estimate network only generates the depth prediction result once. So to generate the consistent global map, especially the scale, we refine some maps according to the motion estimation of corresponding keyframes from the SLAM system. Here we show the compression in this figure, where the depth maps are built by surface mapping using stereo cameras, GEM using LiDAR, and our work using molecular camera. And we can see that our method can produce denser point cloud. This figure shows the global test map of KT synchronous 06 of our work. And this one shows the depth map of KT synchronous 13 of our work. Here we show a video of our work. This is the mapping on the KT synchronous 0. The top image is the current frame, and the middle image is the keyframe, and the bottom image is the deep depth prediction. Because the depth mapping is too large, so we did not directly show the depth mapping here. And this is the sparse mapping from the OpsLab tool. Here is the mapping on the cases increase 13. And here is the generated depth map on KT06. Yeah, because the map is too large, so it's not easy to control this map. And this is the depth map on KT16. Thank you for your attention.